We got everybody here who's coming, I guess. But I see somebody who isn't here. How do you like that? Now, that's an old philosophical question, isn't it? Whether you can see somebody that isn't here. I remember arguing in Princeton with the graduate students for hours and hours, the philosophy students, as to whether what you were talking about when you said there was no chicken in the icebox. Yeah, well, it's philosophy.
So much for you. You outgrew that phase.
That's why, yeah, I have nothing to do with philosophers ever since. We thought that it was possible that there's still people who don't appreciate the difficulty of this thing with the boxes, and so we'd like to divide you into two groups. Those who are perfectly confident about it and don't want me to go over it 16 more times, and those who would like me to go over it, well, at least 2 more times. So can we, we're going to divide this thing up, and we'd like to know how many want me to go over it a couple more times till they really fully feel the difficulty. All right, we have 2, 3 customers, something like that. So what we'll do is that Ralph over there, who's an expert and my assistant guru, will take care of you. In the meantime, the guys who've been asking me very technical questions about perturbation theory, calculations, and other matters of this kind will have a chance to talk to me. Because we have such a difference in the backgrounds of people, we're going to separate temporarily. So the ones who are having trouble before will catch up and see why it's interesting, because that's the whole purpose of this, is to understand that. If you don't understand that, we're not going to understand anything else. I mean, there's no problems. So that's the essential thing. After that, it's very easy. It's going to be easier. It's just like climbing a mountain, and from then on, it's to get a view. You see the view, and now you climb around down on the ground and have fun. So that's what it is. But we have to get you up to the mountain, right? So Ralph will help you climb to the top of the mountain. In the meantime, these guys who think they're there already will waste time by answering the technical things and complicated things, so which the others won't be interested in anyway. All right? So can we do it that way? So he's over there.
I'd like to just go out to the tape.
All right. How about that? So those who are having, you're not going to miss anything, in other words, because it's just going to be some.
Specifically the problem with 2/3, why is 2/3 so
Yeah. So we'll just take care of that, and the other ones will be. We'll talk about other things, please. Then I'll come back when they're all back, all on the mountain. Then we'll go back to the top of the mountain and show what the views are from there on, okay? So the present questions would perhaps be best if they're not directly attached to this question of the 2/3. We'll delay those until our friends come back from the mountain, okay?
Brownian motion.
Oh, Brownian motion. That, of course, is fun. It's you mean, what do you want me to do about it? You know about it?
I know a little bit about it, and I was thinking in terms of what you said yesterday about, well, the reason it came up to mind was you said, well, the atom doesn't have to act the way we act.
Yes.
On a side because of different scale. And then I was thinking, well, where would randomness be in the cell? And I was thinking of diffusion.
Living cells, you mean?
In living, yeah.
Yeah,
In terms
right.
of biological process, I was
Right.
thinking of diffusion.
Right.
And I reformulated the question of that by saying, talk about Brownian motion.
Yes, there's a kind of randomness, but that randomness is not involved in quantum mechanical randomness. You're quite aware. And it's due to the complexity of things, that there's so much stuff and the atoms are bouncing against each other in a kind of chaotic manner, so that for example, a liquid like water, the molecules are, we can take a normal view of molecules as little balls or little shapes of different kinds, and all the same kind, actually. They're all water molecules. And that they're piled together and jiggling all the time next to each other. And this perpetual jiggling is molecular motion. Brownian motion is observable. So it's possible to see this jiggling if you put a small particle, very fine particle of dirt. As a matter of fact, I did it with toothpaste. It's rather nice with toothpaste. If you haven't got a very powerful good microscope, it's easy to see. If you put something like toothpaste or something that's a little powder in it, then the very fine particles keep jiggling about all the time under the microscope perpetually. In the case of the toothpaste, they are flat the one that I happened to have, were very good because they were some kind of flat little crystals. And my microscope wasn't even big enough to see them. But because they would turn and the light would come just right, it would reflect. And there'd be these little flashes all over. So it was kind of, but it's easy with a good microscope. And it's very much like, I haven't seen this for years, but there used to be sometimes tremendous push balls that they had, enormous ball, great big thing, and they put it on a field with people trying to push it to some direction, the other team is trying to push it the other way, and the whole ball moves, and there's this crowd of people underneath, all pushing one way or the other, and the ball just jiggles. And if you look at it from a distance, you could imagine it was so far away you couldn't see the individual people, but could still make out the little ball. And you'd see this little ball jiggling, from which you can infer that the people are jiggling. So in the same way, what you're looking at is a very large mass of atoms when you look at a particle that you can see, because a particle you can see even in a microscope is a billion atoms or so. It's a great big thing. But it doesn't stay put because it's being bombarded all this time by the little atoms, and it therefore jiggles a little bit, and that's called Brownian motion. It was discovered by Robert Brown, a biologist, that when he looked through a microscope, he saw this jiggling motion. And being a biologist, you would think that he would decide that this motion that he saw must be a form of life. But he was a good biologist and made the necessary experiments and ultimately discovered that the motions even existed in the water that was enclosed in a quartz crystal that you could get from the ground that had been there for millions and millions of years. And he looked in, it was still jiggling inside there, so he concluded that couldn't be life, that was a universal phenomenon of nature. And it is, that we look very calm, we look at things, they're permanent, they're stationary, but as a matter of fact, of course, they're made out of piles of atoms which are always jiggling. Our eyes can't see the delicate jiggling, but that is a way that you could make a random generator. You could amplify such jiggling. The electrons in wires jiggle too. Everything's jiggling.
Good noise generators.
And that's, yes, that's right. And so they make electrical voltages which fluctuating. So if you have a good amplifier, you can get a rushing noise all the time, and it's easy to measure, and so on. As a matter of fact, the first determinations of the sizes of atoms was made by measuring how much of the jiggling there was, because you can imagine, you can see that how much this thing wiggles depends upon how big the molecules are and so on, and how many there are. So, of course, in the beginning, when there was a theory of atoms, there was a lot of evidence for it, but there was no way of measuring or estimating how big they were at first. The first estimate was made, I think, by the intensity of the blue of the sky, which is curious, but the more accurate one is the one on the jiggling. Einstein made a lot of the mathematics for the theory of Brownian motion, this jiggling, and these equations were used to compare to experiment to determine the sizes of atoms. Since then, there are much better ways of measuring the sizes of atoms. What else can we say about the jiggling? Do you have any other points? Yes?
I mean, I don't want to get too technical.
You can now, because we've got all the untechnical people.
When I was a student,
Yes.
it was an experiment I was to set up for the dualismus of wave and particle. I wonder how that is today. It's a two-slit pulse.
Yes.
You know, if you have one slit.
Yes, I know. I want to discuss the two-slit experiment in detail later on, a few days from now.
Because
In
I
all
was actually
detail.
setting up the counters.
Okay.
You know, and I was.
Yeah, well, we're going to describe that very experiment, and therefore, if you don't mind, every one of your questions, I always seem to put off. But let's say it this way. They're very relevant to what we're talking about, and I had planned to talk about them. I'm not going to leave you off at the end. I'm not cheating you. Yes?
Okay, so my question yesterday was in
Yes.
regard to it's not clear to me why
Yes.
Feynman diagrams should actually manifest when we look for them.
Why
Because you know, the actual exact solution is an infinite sum that we can't do of all the terms.
Right.
In theory, so why in nature do we find the terms?
Because we're finding the answer to something. Let me show you something, okay? Suppose that the right answer to a mathematical problem is 1 divided by 1 minus 1/100. And suppose I don't know how to divide, because it's very difficult. This is imaginary. This is analogy. The analogy is that I have very complicated equations I can't solve directly. But there are certain other operations that I know how to do more or less easily. So, yes, now we could say that this would be equal to 1 plus 0.01 plus 0.01 times 0.01 plus 0.01 times 0.01 times 0.01, which we write as the 3 times, you know, that's the cube, and so on. Now the fact that, and so on, forever. It's never correct if I stop anywhere. But if I keep on going, let's say it goes 0.1 times 0.1 times 0.1 times 0.1 4 times, or you know what this cube means, I presume. 4 times, and then it goes 5 times, and so forth, okay? Now, if I wanted to see whether my theory agreed with experiment, so I measured something that the theory says is this big, all right? But I can't really calculate that because I don't know how to divide. You understand it's an analogy. Of course I know how to divide. But I do know how to multiply and add. And so I would measure this. Let's say I'd measure this and I'd find out the result was 10103 or something, whatever. I want to know if it agrees with experiment. I mean the theory. Let's say it went to here. That many places. That's not a decimal point. That means I got it that accurate. Okay, I got it accurate. Yeah, right. And these are significant. I measure it again and again, and it always agrees with that. Now we want to find out if it's correct. Then we could do it this way. We'd say, well, if it was a sloppy measurement, the answer is 1. That means I drop all this stuff. But I could do better by adding another piece, which is the first piece. But the next piece turns out, if you multiply it out, to be double 1. And the next one, if you worked it out, no, 0.1 times 0.1. 4 zeros, 6 zeros, it's 5 zeros and a 1, and so on. Now maybe to make the analogy better, it gets harder and harder to calculate the... it's hard for me to multiply. It takes a lot of work. Here I have to do more multiplying and more multiplying, okay? So I can only do a few of these terms. Nevertheless, you see, if I do a few of them, I get an excellent approximation to the answer. So you say, why is it valid? It's valid for the following, to leave out some terms, when really the correct answer is the sum of all the terms. The answer is that the higher terms are contributing less and less. We hope, anyway. We can't calculate them exactly. We're not going to compute them exactly. We're going to stop somewhere. But by a mathematical argument or by guessing or by noticing how each one is going down so well, we suppose that the higher ones are smaller and smaller. So if we forget only the first 4, say, then we would get an answer that was presumably rather accurate. We could estimate that the next one is 100th time smaller than that, perhaps. Of course, all these estimatings and so on are unnecessary. We actually can carry it out in this example, but it's by analogy. We imagine it's hard to do all the arithmetic. Then we would say the answer is 101001 and could conclude, for example, or 01, let's say, and could conclude from this example that it disagrees with experiment. Or if it agrees, it depends on what the experimental result is. It could be agreed. It could agree. The point is we don't have to calculate mathematical quantity exactly. If the theory is complicated, we have other mathematical rearrangements which are equivalent. That's all it is. And the perturbation theory, so-called, with the diagrams, is simply a way of calculating the successive terms of a series like that.
That's clear to me. I'm not clear why the specific terms manifest.
Because we started with something that we know here, a formula that produces these terms. That's what the theory is.
The way I'm hearing the question is,
Each one of those terms
Yes.
is a Feynman diagram, and he's asking why should the individual terms manifest as physical process?
They don't.
Each individual term.
All the terms are there.
Like a particular, one of those terms might be a particular kind of scattering.
No. A particular kind of scattering is the sum of all the terms. All the things are happening when there's a scattering. We have broken it up into elementary subplots to analyze it. Each diagram represents a a piece of an analysis. You could say in this case, if you wanted to, you could say, this is called a Schlankus. Okay, now the theory is complicated. It says any number of Schlankuses can occur. I can analyze it by saying either there are no Schlankuses, the contribution from the no Schlankus effect is 1. The contribution from the one Schlankus effect is 0.01, and 2 Schlankuses is 0.001, and so on. But in any real situation, there's an arbitrary number of Schlankuses, and they're in the formula here. There's,
If we look at the decay of a neutron,
yes.
The decay of the proton, electron, neutrino.
Yes.
Simple, but there are higher terms.
That's right. That means that the formula for the decay of a neutron is a complicated expression, which is being expressed as a sequence of approximations.
Yes, I understand that the first order term
Yes,
is a Feynman diagram, and the second order is a second order term is another more complicated Feynman
that's
diagram.
right. It represents a more
Right,
complicated
and we look in nature and we find the first order term.
plus the second order term,
The
plus
second order, whatever it is.
we plane them all.
Okay.
We find them all as nearly as we can measure. If we only measured a certain number of figures, then I can't be sure that these are here. But they were invented because this is what we were trying to express. We know this side and we represent it this way. And we just say there are these terms, and these terms are left out because they're so small. I don't know what the problem is.
Yeah, I know.
Well, maybe we can talk together sometime and get it clearer. Have everybody back or no? I see there's still somebody working.
No, yeah, we're all back. He's just getting some.
Oh, okay. So you're all back. You mean you've all been educated? Everything okay? Oh, great. Well, that was easier. He said it would take a half an hour. But apparently you were closer to understanding it than he thought, or he was cleverer at explaining it, or else he gave up in despair.
Maybe an even higher order terms.
Right. Okay. Well, now that we all are together on it and see that there's something deeply puzzling about it, I review the phenomena for just a moment and say a few words about it and tell you things. The idea was we discovered this, that we can get 2 boxes, each of which has 3 buttons on it. There's 3 buttons, which we say 1 or 2 or 3, and we can push a button, and it lights a light, which is either red or green. You mind I change the color from red and black? The black light is a little annoying analogy. It doesn't light, it's no good. So here's the measuring light that comes out. You push, yes, you could do it many ways. You push this and the light's red or green. This is button 1, button 2, button 3. Likewise on this box. And just to review, once finally more goes like this. The boxes are set up and I give you charges for them, or I give you the boxes. It doesn't make any difference. I have, once they were together, they can be taken anywhere. Now, it goes like this. If you push any button here, the light will light up either red or green, and it's about 50-50. If you push a button here, and then push a different button on the box, then the light agrees with the other one only a quarter of the time. That is, if this one gives red, and then you push the other one, this will only give red a quarter of the time. Or it gives black, the opposite color, 3/4 of the time. We've said it both ways, right? And that's very curious. If there were, well, we've explained the curiosity of it for too many times. Now the situation is here that this box has the same prop, that this box will always agree with this one. If you push a button on both of them, then the buttons will give the same color lights. This doesn't have a light yet, so therefore it won't work yet. All right, I'll put the light on it. Good. Now, if you push button 2 on both boxes, then the lights are both red or both green. They always agree with each other, no problem. And, but what's odd is that if you push a button 1 here and get red, and push button 2 here, it'll be black 3/4 of the time. And after a lot of thought, and much study, we've discovered that that's very strange. Okay? We can get 2/3 of the time without any trouble, but not 3/4 of the time. So I would now like to say what the uncertainty principle is. I said it once before. I'll just say it again to make it clear to everybody who now understands it, what Bell's theorem is and what the Einstein-Podolsky-Rosen paradox was supposed to be. Okay? And a little bit of the history of it. But first, forget the second box first, and think about this first one. If when I push this button I get red and green, then if I push this one and it agrees or disagrees, let's say 3/4 of the time, that's impossible unless, if we imagine there were cards under there or something like that that were set, that when we started out that this was going to be red if we pushed it, and if we pushed this one, let's say it was going to be green and this one green, then sometimes when we pushed a pair of buttons like this pair, we get them to match. And that would be 1/3 of the time because we could pick the buttons in every pair combination. And there are 3 out of all of the 6 different ways of choosing, 3 different ways of choosing pairs, one of them match. That one would give a match, that would give a not match, and that would give a not match. So if I pick 2 buttons at random, I'd expect they'd match 1/3 of the time, but actually they only match 1/4 of the time. The easy example would be if they didn't match at all. Then you would have to say, sir, in either case, that something happens, that when you push this button, if they were red, green, green was a set that they would have made if I had pushed them, then when I push this one, I must change it somehow because the experimental result is 1/4 of the time. So when I push this, the only way to explain that is to have a machine that if I push one button, it changes the ones underneath. Now, if we go to nature and look at it and say, well, what happens if I looked at all the buttons at the same time, that I pushed this and got the result and pushed that and found all the results will always repeat. For example, nothing would ever change, then I'd be in a pickle. So, but it is true that we're only allowed to push one button at a time, and furthermore, it does turn out that when we push a button, let's say this one and gets red, then this one is green, say, and we push this one again, it's no longer red. So we have experimentally noticed that it is true. It's quite possible and perfectly true that we could imagine it this way, that when we push the buttons, they change the colors of the other lights. I remind you, if you push the same button again and again, it always checks out the same color. I start out and make sure this is red by pushing it 8 times. Then I push this one, it's green, it'll stay green all the time, say. Then if I push this, it's possible that it be green now. Okay? Otherwise, I'd never be able to explain this 1/3. Yes, yes. If you push the same button, it never changes the result if you push it again. You push the same button again.
If you wait a while, it'll still be.
Yeah, yes, in a particular circumstance. Obviously, this is set up for a particular measurement. Yes, it can be made so that it doesn't, in general, doesn't change, and you can push it as much as you want. There are situations where things change, but there are situations where they don't. Yes, you can push it as many times as you want in succession, and nothing about that button changes. We don't know what's happening in the other ones because we can't see. And when you push another one, then you see it's changed. So you could still imagine that there was sort of potential or cards underneath there or some kind of thing that determines what color is going to be. But now we have a new rule that when we push it, it changes what's under the other buttons. And furthermore, we can't assume that it doesn't change, because if we assume it doesn't change, we're going to get in trouble with the 1/4 result, or the 3/4. So therefore, we would have to say that if this theory, well, experimentally it's right, the theory is right, but when the early days when it was first discovered, all the experiments weren't done yet. But when the theory came out that would predict results like this, it was obvious that it was necessary for such results, that if there were such a thing as the potential lights that were going to light, I mean the potential cards under there, that by pushing buttons you're changing the results that you would get for the other buttons. And experimentally it does turn out, just like we said, it's all right, everything's okay. If you push this and get red, then you push this and get green. It is possible when you push that to find it's changed. In fact, it's necessary that you find it changed, because if we keep on thinking about this, we would get 2/3 otherwise. And we don't, for 2/3 of the time, there would be different They would change, and 1/3 they would be the same. But it's rather 3/4 than 1/4, so we have to have it change, and God, thank God, it does change. But that's a very simple view then. There's nothing wrong with that, but to say that there were these things were under here, but they changed. Now to say there were things under here, that is, ahead of time there's a potentiality to be red or green without looking at it yet. We can talk about such an idea. We're going to call a classical view. That means an old-fashioned view. And what Heisenberg said was that the old-fashioned view, if it's tried to be maintained at all, would have to have in it an additional new feature that it shall be impossible to determine what color this one would be without changing the potential color that the other one would be. In other words, by measuring that, by pushing that button number 2, you've got to change the colors under number 1 or 3 if you wanted to picture it with color. And we see why we have to do that. Otherwise, we would get 1/3 and we wouldn't get the result today of experiment and of that time of theory. Historically, however, Heisenberg's statement wasn't measured with this particular box business, and he didn't have this nicely, which took 40 years of patient thinking to get the simplest possible example. He had a more complicated example, which was measuring something called a position of a particle, which is an idea that anybody classically would think. A little ball or an electron or a particle would have some kind of position, and you can measure what it was. It would be a number. It would tell you how far it is from the east wall. But 3 numbers if you want, plus that wall, plus that wall. But let's talk about motion just this way. There'd be a number which would tell how far a particle was from a wall. There was another thing one could measure in classical physics, which was something like the speed. Actually, it's called the momentum. It's the speed times the mass. It's a thing that tells you how well it coasts. And you could also measure the momentum. Obviously, you can measure its speed, and you can measure it as accurately as you want, and the position is accurate. Perturbation theory, calculations, and other matters of this kind will have a chance to talk to me. Because we have such a difference in the backgrounds of people, we're going to separate temporarily. So the ones who are having trouble before will have caught it, will catch up and see why it's interesting, because that's the whole purpose of this, is to understand that. If you don't understand that, we're not going to understand anything else. I mean, there's no problems. So that's the central thing. After that, it's very easy. It's going to be easier. It's just like climbing a mountain, and from then on, it's to get a view. You see the view, and now you climb around down on the ground and have fun. So that's what it is. But we have to get you up to the mountain, right? We'd like to divide you into 2 groups. Those who are perfectly confident about it and don't want me to go over it 16 more times, and those who would like me to go over it, well, at least 2 more times. So can we, we're going to divide this thing up, and we'd like to know how many want me to go over it a couple more times till they really fully feel the difficulty. All right, we have 2, 3 customers, something like that. So what we'll do is that Ralph over there, who's an expert and my assistant guru, will take care of you. In the meantime, the guys who've been asking me very technical questions about perturbation, so Ralph will help you climb to the top of the mountain. In the meantime, these guys who think they're there already will waste time by answering the technical things and complicated things, so which the others won't be interested in anyway. All right? So can we do it that way? So he's over there.
I'd like to just, go out to the tape.
All right, how about that? So those who are having, you're not going to miss anything, in other words, because it's just going to be some...
Specifically the problem with 2/3, why is 2/3 so
Yeah, so we'll just take care of that. And the other ones will be, we'll talk about other things, please. Then I'll come back when they're all back. Good question, isn't it? Whether you can see somebody that isn't here. I remember arguing in Princeton with the graduate students for hours and hours, the philosophy students, as to whether what you were talking about when you said there was no chicken in the icebox. Yeah, well, it's philosophy.
So much for you. You outgrew that phase.
That's why, yeah, I have nothing to do with philosophers ever since. We thought that it was possible that there's still people who don't appreciate the difficulty of this thing with the boxes, and so We got everybody here who's coming, I guess. But I see somebody who isn't here. How do you like that? Now, there's an old philosophical